Well, let's talk about power, I guess, for a bit. Um, well, you teach statistics classes. Is power like a big? Is that a big part of what you teach or in your research?
It is. It's a really important consideration. I do talk a lot about power in the courses that I teach. I have not taught an undergraduate course in a couple of years. Probably the chapter on power, which we address right after the one sample Z test, probably the undergraduate student's least favorite chapter, because of the conditional probabilities that one has to tackle to understand power. And yet
Yeah.
it is a central concept. And, power, effect size, type 1 error rates, and type 2 error rates are all intimately intertwined. And you can't really come to grips with any one of those notions, one of those concepts, without coming to grips with all of them. So they're deeply intertwined, and it's not a subject that's an esoteric sort of secondary consideration. It's not, oh, we're worrying about distributional assumptions for tests that are robust to large violations of those assumptions. We're really talking about a core concept.
Yeah. It's funny you say that because a couple months back, we were discussing of starting this video series on statistical power, just one video, right? So I started initially doing that, and I was like, wow, I can't really explain this in 10 minutes without revisiting prior concepts. Like, I need to do types of errors before this. Like, okay, now I'm doing type of errors. Hey, I kind of need to explain the known alternative hypothesis way before that. So it kind of ends up snowballing to this 6 video long series, and at the end, you kind of get into power and how to have it quite, adequate power not to make those type 1 type 2 errors. So
It was quickly like, all right, write the book now, and then we'll piece it back together concisely. I had I had a good intro stats course on the graduate level. I had some on undergrad level too. Power was probably one lecture. I don't blame them for not spending that much time on it, because I feel like most of the research I read is just kind of there to cover your bases. Like, hey, did you do a power analysis before you started this? Or before you said you needed XYZ animals? Like, it was just like a shield to protect yourself from reviewers. You're like, oh, let me just go back and pretend I did one. Rather than, I think maybe I have a better appreciation for it now in order to like why it is important, and why you should actually care about it.
Well, in defense of that, post hoc power analysis, if you're working routinely in the same experimental paradigm and you have an intuitive sense of the rough effect sizes that you're expecting to detect, and you've seen what sample sizes have worked in the past, and you plan your future research based on those previous experiences, one can have a native intuitive sense of, yeah, we're going to need a little bit larger sample size than normal, or oh, we can get away with a little bit smaller sample size in this particular case because you have a reasonable set of experiences that guide those decisions. When you start asking for funding from external sources, however, it's pretty helpful to have done an a priori power analysis so that when you go to ask for, a couple $100,000 in a small grant or a couple $1 million, that, the people giving you the money know there is a reasonable chance, if there is, the expected effect out there, that you'll be able to detect it. And it's sort of a shock sometimes when you're exploring new experimental paradigms and you think, oh, Well, I'm using my past experience, and having, 20 people per condition should be fine. And only to discover one of your measures is not as reliable as you'd like it to be. One of your measures has a lot more noise and measurement error in it than you'd like. And all of a sudden your effect sizes are a whole lot smaller than you thought because of that attenuation due to unreliability. And it's really disheartening to realize that you had less than a 50% chance of detecting an effect, and that instead of spending, hundreds of thousands of dollars conducting the research, or even tens of thousands of dollars conducting the research, you could have just flipped a coin. And, simple coin toss. Oh, yeah, hey, there's an effect there. It's really sobering. It's not a good moment in science when you start realizing, I didn't find the effect I was looking for. And now I discover that I had less than a 50-50 chance of doing so. And so the question remains unanswered. And we don't have any sort of definitive, no, this isn't out there, because we still don't know. We didn't have a good chance of detecting it.
Yeah, on that note, I experienced something similar when we were trying to design this new experiment that kind of had no data, right? And my PI was like, do a power analysis, see how much sample size we have. It's like, okay, I'm making an educated guess on the effect size here. I have like 0. There's nothing out there. And then I'm just gonna plug in some random number. Here's the sample size it brings out. You do the experiment, and then the power comes out to like 0.3 or something like that afterwards. And it's like, I just spent like 5 months.
Or you find out, you're like, oh, I need like 1,000 samples. Yeah, this isn't going to happen.
Oh, man.
Yeah, it leads to some craziness. And when my sister was in graduate school, and we overlapped for most of it, she worked in reproductive physiology, and an N of 1 for her would take weeks and weeks to collect. And she had to maintain a breeding rabbit colony to provide the ovaries that she was doing her research on. And so when we started doing power analysis for the analyses, and she just started laughing and couldn't stop laughing. And she's like, I'll retire before my research is finished for my PhD. Maybe I'll have children or grandchildren who want to, continue the cause.
Do you think then, does that invalidate that research because there's just so few sample sizes to even go off of?
No, it doesn't invalidate the research at all. What it means is that one has to be very, very careful to consider a set of hypotheses that are testable, and that one has to exert a whole lot more experimental control and control the extraneous factors, rather than saying, oh, let's add this as another factor in the design. So she ended up doing in vitro work rather than in vivo. So she had to do surgeries on her rabbits to remove their ovaries, and then insert a cannula into the ovarian artery to perfuse it, and then collect hormone measurements continuously from this disembodied ovary so that she could keep it in completely controlled conditions. So we had to pare down the original thoughts about the research to do something very, very circumscribed. And it was a very, very cool research.
Does that control, though? I would imagine that just help, maybe not just, but that just helps you keep the variance down. You still just have that one sample.
Yeah, and she wasn't doing anything with N of 1, but she was working with sample sizes of 15, 16, and
it's actually
not 120. That I think 120 was one of the first numbers that I came up with for the multi-way ANOVA that would have been the really beautiful way to address her multiple hypotheses. And ultimately, the decision was made to use non-parametric statistics, because we could get at some decisions with smaller sample sizes and not have to worry about distributional assumptions.
Getting into that, part of my research a lot of criticism into one of my technique by a lot of reviewers are you only have one replicate. But then if you look at my measurements, the number of measurements I'm taking like 1,000 measurements at once, you know, so that should be considered a factor, but they just don't look at that at all. And even if you're trying to argue that, you cite certain papers, and we've had this problem many times by many reviewers. It's okay. It's still not, it's like every time we submit a paper describing this technique, we just get the same type of answer. You need more replicate. You need at least 3 replicates. Like, well, you know what? My measurements are really large, and that really helps with my variation. So no, thank you.
Yeah,
I guess that's,
you know, the shift in paradigm is tough. It's difficult in you know, techniques shifting over time. It's difficult when statistical techniques shift over time. And when I was in grad school, Professor Don Delaney made the observation in philosophy of science course I took with him that just really struck me. And that's the bigger contribution you make to a field, you know, theoretically or methodologically, the bigger an impediment you will become eventually to the field moving beyond and advancing further. So it's not really a surprise if, you know, reviewers are steeped in a particular methodology that they would, you know, heavily critique something that uses a different methodology that is making, you know, a different basis for the inferences that are being drawn.
Yeah.
what is it? Die a hero, or live long enough to see yourself become a villain. But Vin, in that example, though, I guess maybe my question is, what's the sample, or what's the population? Because what was their argument? Like, you're just pseudo sampling. Like, you know, if you measured my blood multiple times, you don't have multiple samples. You just have like technical replicates of me.
Yeah.
So for your technique, like what?
Well, in that specific technique, right? When we explain the kind of experimental technique, it's essentially a probabilistic model of 2 bonds forming between protein, right? So we have 2 cells essentially, and we have proteins decorated on them, specific proteins that we're testing, and we want to measure their binding rates. And let's say I have a mutation on one protein that affects the binding rate, right? So we bring the cells together, we pull them apart, and our readout is a force-dependent readout. So if the bonds were to rupture fast, that means the mutation have had an effect on the binding rate. So we're doing this thousands of times, right? And yes, it's one replicate, but each time that our estimated mean is getting smaller and smaller and getting nearer to the true population mean of the sample distribution. So that should be fine. So that is what our argument is. And for the past, the technique was developed like 7-8 years ago. For the past, like every single time we submit a paper using this, it's just, the reviewers always say that, do more replicate. And we just try and explain it's not how it works. It's a different type of model. You know, it's more, we're not looking, the readout is very specific, very niche for this specific technique. So it should be considered as kind of a different case altogether. I don't know what your thoughts on that, Matthew.
Well, you know, it sounds very much like the difference between doing within subjects or between subjects manipulations. And so you're describing these, you know, multiple replications within a particular cell line or a particular condition, and that those are allowing your standard error to become quite small and give you a great sense of confidence in the means that you're estimating and using ultimately for the inferences that you're drawing, and that the reviewers were wanting more of a between subjects kinds of comparison where you would have, you know, another lab replicating this or replicating with, you know, different sets of proteins, different sets of cells. And, you know, That's what happens when a psychologist tries to follow some biochemistry. So I'm not sure if I'm really understanding it. I'm just
No,
looking at
that
the
yeah,
analogy.
that's exactly what some of their arguments are. And it's funny because we do have control cells where here's our control protein. We know exactly how they behave in comparison to our tests. Look, take that into consideration as well, right?
What's a replicate? Would another replicate be another pair of cells?
Another replicate would be, yeah, a whole another set of cells in which, you know, it takes like weeks to prep. So
But
time is a factor here.
You don't care about individual cells, right? You just care about proteins.
We care about the exactly. We care about the protein interaction. The cell is a vehicle, and that's like the exact point we're trying to convey here. The cell is just a vehicle for the protein to sit on. We're not the actual thing being measured is the force of disruption, the binding kinetics. So
it's just a difference in opinion on like what your populations and samples are then.
Yeah.
Maybe,
yeah.
How did you do your power analyses for that? How did you figure out like you're done? Like your standard error keeps getting smaller and smaller. Do you just like do that forever? Or
yeah, I mean the
like
overlap.
I'm tired today. We're good. Today's over. Publish it. Move on.
I'm going.
No one's gonna look.
Like Matthew said, I'm just going by past people have already done conducting these power analysis. It would take me forever if I would just continue that. So I'm just going on past analyses, obviously. But essentially, our variation from the estimated mean is so small that we'll just have to if there is a true significance, right? A true effect, and we find that the estimated mean will be so close to each of those populations that will be distinguished anyway. So then there's kind of really no point in trying to repeat that again if we clearly see two separation.
Yeah, you don't need extra to figure that out.
Yeah. Well, it does bring us back to the topic of power. And so if we have the control group, the control cells that do not have any particular effect on binding, and the pair of cells where the protein have a mutation where it does have an effect on binding, if we do a reasonable number of replications to get the standard errors small within each condition, we'll be able to detect that effect as significant. And so, you know, the role of power analysis there would be a priori to make sure that we did enough replications to be able to detect that kind of effect. With phenomenon that are not all or none, where there is an effect or there's not an effect, when the effect size is there a minuscule difference in the binding reactivity versus a semi-minuscule versus a small versus a semi-small, medium, large, super large, huge, gigantic, enormous. If there's this full range of different effect sizes out there. If we pick a sample size that's too small, we can only detect those ginormous differences. And it has to be just a, you know, smack you upside the head kind of difference. The issue, and this is where some people can get themselves in trouble with power analysis, is to not conduct formal power analysis, not consider what is a reasonable effect size, an effect size that's meaningful, and how much of a change in this binding action do we need to observe for it to be important for, you know, use in basic research, to be important for use in drug design or, you know, other applications. If we're just wanting there to be an effect so we can publish and move on or defend a dissertation, then we keep increasing the sample size and keep increasing the sample size, making those standard errors smaller and smaller and smaller until we have this tiny little nano difference that is completely unhelpful to anyone wanting to, design proteins that will have, a superior binding or binding that breaks apart more easily, if the difference between bound and unbound is so tiny that it's not meaningful, we can detect it. We can keep increasing the sample size until we can find an absolutely absurdly small effect as significant. And when I, talk to my students, I'll say, IQ tests may measure something other than intelligence, but they measure something. And if we fill the stadium with, 80,000 people, and we give the East half and the West half the same IQ test, whatever it measures, we'll probably find a difference in scores. And does it mean that the East half is better at solving problems? Probably not, because 1/100th of an IQ point with those large sample sizes of 80,000 is enough to be statistically significant. But the effect size is so small, I can't really conceive of an intellectual problem to solve where 1/100th of an IQ point difference would allow you, almost all the time to solve the problem. But with 1/100th of an IQ point less, you almost never will be able to solve the problem. The effect size, when all else is held equal, the effect size for one study that has p equals 0.06 and another study that has p equals 0.049 are going to be very, very similar. And we would not interpret those effect sizes terribly differently. And so the problem with continuing to add, samples to increase your sample size, decrease your standard error, and achieve statistical significance is that with somewhat unlimited resources, and I know that's not the case, but with unlimited resources, you can always get a large enough sample size to reject the null hypothesis. If you do so, if that is your practice over a lifetime, or if a discipline adopts this practice and everyone, continues to increase their sample size until achieving statistical significance, we have no falsifiability. If there's no way to falsify or find a lack of the effect you're looking for, it's not science. It's now a matter of belief. It's like, I so believe in this effect, I kept collecting data until I had proof.
Until I have less than 0.05. It's like, hey, you're,
and of course,
type 1 error.
If this is the true mechanism, then that effect size that you end up reporting after you've gotten an obscenely large sample size is going to be very small. And people are going to look at that and think, that's not terribly practical. That is not going to lead to a meaningful difference. And so then your sample size ends up becoming a proxy for your effect size. And let's just calculate the effect size.
Okay, Vin, let me pick on you for a second. Allow me to pick on you. How does that differ from what you just described, though, where you would keep doing multiple measurements on that replicate, and you would see that your standard errors a better idea of like the true effect? Isn't that the same thing as what we just described of like, I'm just going to keep measuring this until I get an effect?
For that, the way I see it, you're looking at multiple comparisons, right? In my study, even though I'm having set like a measurements of 1,000, that's still just one comparison.
Like you're not doing a comparison at like measurement 900,
I'm not like
920.
Exactly. I'm not doing one comparison, having this p-value, doing another comparison, having another p-value, and then keep doing that until I'm finding a p-value low enough. That's just committing a type 1 error, right? You're just trying to find that one chance, even if it's very low, that you have a statistical significance. I'm just saying, I'm going to do one comparison, and I have a shit ton of measurements. And based on all the previous controls I've done with test proteins, to guide my effect size. That should be enough.
But isn't that the same? That's the same. Okay, I'm making a couple of assumptions here. I'm assuming from all those other things, though, you were like, well, how much do I need to find an effect, to find significance? And now that is now guiding all of your future decisions on how many to do. So it comes back to, I don't think it's that big of a deal, but it's still the same thing you're doing, right?
It still is, but it kind of isn't as well, right? Like this gets back to the same thing. I'm doing one comparison. If the probability of landing that one comparison is extreme, it within the true population mean and allow me to reject the null hypothesis is high. It should be high based on the previous experiments, right? Then that should be fine. Like again, I'm not doing one comparison and for this specific protein, this specific mutation, and then continue doing it, even though all the comparisons I've done in between tells me that there's no difference, but I keep doing it until I see the significance. I'm not doing that.
Right. It sounds to me then, as you're describing this process, that you had a very fixed effect that you were looking at.
Yes.
And that the effect would happen or not happen. And so you didn't have the risk of having such a large number of replications that even a minuscule effect would be observed, because your effect is either there or it's not there. So if that's a dichotomous effect, the effect size is either 1 or 0, because you either observe it or you don't. And I think that's where what you did was sort of an empirical power analysis, because you had a fixed effect that you were looking for. How many replications does it take? Well, 1,000 has worked well for other people. And in the experiment you're describing, 1,000 worked well in your case as well. So it sounds like that was an example of doing an intuitive power analysis, and that, you didn't have the risk that is so prevalent in my field, which is that, these effects are not all or none. They are, very nuanced and, continuous in nature.
Yeah.
So I think that sets a clear difference.
Yeah.
For like a purist though would say like, well, like numbers are numbers, like the distribution is what it is, so like I don't care about what your field thinks. You just don't have the power.
Oh my gosh.
I'm not saying that's how I feel, but I just like whatever, as long as you report what you did, I don't even care. As long as we can figure out what happened.
I have
P hack away.
I just want
to know what you did.
P hack
So,
away.
I guess so. A watershed moment, that's way too dramatic. A new realization I had is, like people say, was the study adequately powered? Thinking that there's like one number of power for an entire study, but it's per measure, right? So yeah, you said this earlier, Matthew, like some of your other measures might be horribly underpowered to be able to make any conclusions. So I guess in mine, at least, it's just kind of this like, check the box. Was the study powered well? It's like, but powered to do what? And what's of interest to you, and what's of interest to the principle irrelevant to someone else going to read that. They're like, oh, I'm actually interested in all the stuff you kicked over in supplemental, and for these things it is powered well enough. I mean, maybe that's the point of why you should move to effect sizes, because then you could just compare across all of them easily.
Yeah, and of course, effect sizes sound like the best thing since sliced bread, because you create a numeric index. It allows you to compare results from different studies using different paradigms, different statistical analyses, can generate the same effect size, or an effect size in the same metric. Many of the effect sizes that are out there, effect size measures, have equivalents and formulas to translate from one to the other. And so it sounds great. And so if we say screw null hypothesis significance testing, screw the p-value, let's just report these effect sizes for everything we do, and that's all we need to know. Great. We've now reduced our science to a descriptive one where we can describe how the effect size, and then, oh, well, was that effect size significantly different from 0? And now we're right back to square one with not having a basis for making a yes or no decision. We let's go continuous. Let's have this, range of effect size from, 0 to 1. A lot of them are geared in terms of proportion of variance accounted for, and proportion of variance explained. But how big is big? We come back to that same problem. So it's not a panacea. It's not going to fix science. It's not going to be a cure-all where we blindly compute and report effect sizes and throw all the rest of it out the window. They need to be used in conjunction.
You could still generate confidence intervals though for those effect sizes, and I guess that's your point. You come back to
what is
testing. I guess so. A problem that we will encounter forever with our company is we are 90% of the time coming in after all the research has been done. Like the researchers who did it, they're not even like at the institution or organization anymore. There's just no going back to do anything different. It is what it is. And yeah, we did exactly what you just described. We did the hypothesis testing and it was like, oh, like everything is super significant. I have no idea what to make of this. And I think that was legitimate. I don't quite think it was like a multiple comparison false positive. Like these were just really different groups. So then we said, okay, well, let's do this effect size thing. But then I think what helped is, we would plot, here's the effect size of group 1 and 2. But then we would also overlay, like, here's the actual power. And we only had 8 animals. So it's like based on your power, if your effect size is in this shaded region, it's inadequately powered to do that. I feel like that helped. I suppose we still did have that problem of like, well, is this one really bigger than this other? Is the effect here really bigger? But I feel like it was so much. We weren't even at that level. We were just like, it increased or it decreased. We don't know. No one else researched this thing. Is this like effect size of 50 real? Which is a crazy high number. I don't know what my point is with that, other than I think it did improve. It was an improvement over hypothesis testing, and did allow us to look at. I guess what I liked most is like everything is unitless and you can compare across. It's like, I don't know if losing 5 pounds is a bigger deal than lowering cholesterol a few mgs per deciliter. Like they're not even on the same scale. And you can do that with effect sizes.
Exactly. And, another point to be made here, when you've got a big study that involves a lot of different factors and lots of things are significant, and we're like, gosh, we don't know what's more important than another. Well, one single study isn't ever going to address all of the questions, all the follow-up questions that are generated by those results. Science is always a series of experiments, a series of studies, and trying to see the pattern. And sometimes we have to take an effect and zoom in on it a little bit and explore, why is that effect as large as it is? What accounts for this effect? And then there are other times when we need to zoom out and, well, can we control for some of these other factors? Can we, consider some of the other issues that might be at play? So, and this is a conversation I have with my graduate students very frequently, usually as I am suggesting we jettison some of the factors to be considered in the design. We're maybe not going to be able to do everything in just one study. Or even just, a couple of studies. You're really outlining a program of research for, about a decade. So, You know, yeah. So when you go to interview for your first academic position, then let's have this conversation again.
Here's my 10-year plan.